and the reference layer exists only on one side. So when the domain wall moves from left to right, nothing happens for a long time. But when the domain wall moves to this side, then you will see a change in signal which will produce a spike. So that's why we call this as a spike neuron. And for neuromorphic computing, we prefer spike neuron because neuromorphic computing is a kind of spiking neural network. So that's how we can prepare neurons. So basically we will be using some magnetic tunnel junction, but with the reading part only at one side of the neuron. Then to prepare synapses, we cannot use the MRAM kind of thing because that can only store 0 or 1. But we'll have devices which will look something like this. So we have a reference layer, we have a free layer, and the free layer, the domain wall can be moved from one end to the other end. And depending on whether you have fully parallel state or fully anti-parallel state or intermediate states, we can have different resistances. And this is what we want for neuromorphic computing applications. And we can change the domain wall position by current. So we can send a current through the ferromagnetic layer and create a spin transfer torque, or we can send the current through the spin wall layer and generate a spin orbit torque for moving the domain walls. Okay, so you can move the domain walls by magnetic field or spin transfer torque or using spin wall effect. So most often in the labs we usually use magnetic field first because that's the easier thing to do. Then when at some point of time we may also use spin wall effect to move the domain walls. In the context of neuromorphic computing, domain wall motion in neuron is called integration. Okay. And in the case of synapse, domain wall motion is used to change the weight because it changes the resistance of the device. And we can use a current, either spin transfer torque or spin orbit torque, to move the domain walls. Okay, so let's do some questions. Okay. Basically, this question you to understand where I am going. Anyway, so to summarize this point, we have learned about that we can use domain walls to make synapses and neurons. And what we need to do as a physicist or material scientist to achieve neuromorphic computing is that we have to increase the tunnel magnetoresistance as high as possible because that helps to achieve multiple resistance state. And we have to find out materials that drive domain walls at low energies. So we can look at materials that provide higher spin orbit coupling, or we can even consider orbital torque and so on, so that we can achieve energy efficient operation of these devices. When it comes to synapses or neurons, we should be able to make devices that shows multiple resistance states. So in this case, the concept of domain wall pinning is important. So that's what I'll spend a few minutes later. And when it comes to neuron, the neurons that we design should be able to demonstrate, leak, integrate, and fire functions. Okay, so this is what I'll be talking about in the next few minutes. So now we move on to learn about synapses. So I was telling that the domain wall pinning is important. So this slide basically summarizes why it's important. So here I show the magneto-optical image of a cobalt palladium multi-layer based domain wall device. So this long wire is what you see as the domain wall device, and this is something that we usually create for manipulating domains. So in this particular case, the color represents magnetization up or down. So let's say white is magnetization up, gray is magnetization down. So we saturate the sample with a positive magnetic field, then we go back to some negative field. So until minus 1854 posted, nothing happens. When I change the magnitude slightly, then there's a sudden reversal from magnetization up to magnetization down. It means domains are not created and the domain walls are not moving. Okay? Or they are moving so fast that we are not able to see precise domain walls. Okay? So this kind of configuration is not useful for neuromorphic computing application. As I mentioned, this can only give 0 or 1 state. We want multiple resistance state. So to achieve multiple resistance state, we have to be able to control the domain wall motion precisely. So for that, we may need to pin the domain wall. Yes.
Sorry, I might be wrong, but the thing is that the white represents plus magnetization and
Yeah, let's say this means magnetization is towards you, and this means magnetization is towards the board.
and they have the same sign
They have the same.
because they're both minus. So is it like the 1854 worsted? Is that like the applied external field?
Yeah. So I'm applying external magnetic field. This is still plus because we have saturated and we have not reversed the magnetization. So this state continues until this point. So the magnetization is up. So when I change magnetization, magnetic field slightly, it goes from up to down.
So you're talking about that
Yeah,
transition point.
Yeah, it goes up to down. So what we need actually is like when we move from 1854 to 1858, probably this much has become black, so this is white. Then we increase the field, this black expands slowly. So that's what we expect. So in a few minutes you will understand.
So it's like you are looking for the switching regime where you just apply a small amount of field and it changes sign.
Yeah, it completely switches. Yeah.
Changes sign.
Yeah.
Okay, and that's why the saturation regime would not work, but the switching regime would work for this kind of application.
Yeah, later
Okay.
wait for a few slides, then
Okay.
you will understand what I'm talking about.
Thank you.
Yeah. So here basically we are not creating any domain wall, and we are not, yes, please.
Actually, you have studied the domain wall motion in the TMR structure. So, is it also possible that we study the domain wall motion in the GMR structures, pinwheels like?
Okay, ideally we should study the domain wall motion in TMR structures, that then we can demonstrate synapses and neurons. But for most of the study that I will show in my presentation, we are only looking at the free layer. So we are not talking about the barrier or the reference layer. So most of the studies that I am showing here are focusing on the free layer only.
Okay.
So you can use GMR or TMR. The problem is in GMR the percentage of the resistance change is not significant enough.
Okay, thank you.
Okay, so we need to control the domain wall motion. So for that we need a domain wall pinning mechanism. So there are various ways in which we can pin the domain wall. So there are magnetic approaches as well as geometrical approaches to pin the domain walls. For example, you can do some ion implantation locally at these regions. Then there will be a change in the magnetic property. So these are the regions that will pin the domain walls. Or you can create a local metal diffusion, or you can locally change the ferromagnetic property by exchange coupling and so on. So there are various ways, and you can also use the geometry to pin the domain walls. But from a practical point of view, geometrical pinning is the most efficient way, I mean, most practical way to pin the domain wall. So the topic that I am going to discuss today will be a geometrical approach. So when we talk about domain wall pinning, what happens is we create an energy barrier or energy valley. So when the domain wall comes to this region, it sees an energy barrier and stops. And when we have an energy valley, the domain wall will come here, see a barrier and stop. Okay, so we have to create domain wall pinning sites. So that's important. So one study that we have recently carried out is a pine tree snap. So in this case, we have a magnetic material which is lithographically designed to form this kind of pattern. So it's called pine tree snaps because it resembles a pine tree. So here we have two things happening. When you send a current, if you have a spin Hall layer, so there's a spin-orbit torque which tries to push the domain walls to the one side. And on the other side, we have Laplace force which tries to act in the opposite direction. I don't know if maybe I should ask you this question first. Can you see the, yeah. So you have two balloons connected by pipe, okay? So in this case, when you release this wall, from where the air will flow, okay? So let me open this question again, please answer. From 1 to 2 or 2 to 1? You cannot see, you cannot see? Nobody can see?
1 to 2.
Okay, the answer is once you open the wall, the air will flow from this small balloon to the bigger balloon. Okay, that's because the Laplace pressure is bigger for this balloon than for this balloon. Okay. So basically the concept that we are using in this synaptic structure is the Laplace pressure of the domain wall. So when we consider this domain wall as the balloon layer, and it has a different Laplace pressure. Okay, so when we send current through the spin Hall layer, there's a spin orbit torque that pushes the domain wall in one direction, and in the other direction there's a Laplace pressure. So as a result of this, when when the spin transfer torque is higher, then the domain wall will be deepened and move to the other side. When the Laplace pressure is higher than the spin orbit torque, then the domain wall gets stuck here. So this is how we pin the magnetization or domain wall in this kind of device. So here we are using the concept of Laplace pressure to pin the domain walls. So first we carried out a micromagnetic simulation. So we have different segments, and each segment has this kind of shape. So one side we have a smaller bit, another side has a larger bit. And because of this different bit, and okay, first we carried out a micromagnetic simulation, and we looked at the current that we need to deepen the domain wall from this position to the other side. Okay. So when we do this, we notice that there is an easy direction as well as the hard direction. It's like when you have two balloons with a different Laplace pressure, the air always goes from one side to the other side. So in a similar sense, in this kind of domain wall devices, it's easy to move the domain wall from one side to the other side, and it's hard to move the domain wall from the other side. So we noticed that the currents are much lower. The current needed to move the domain wall from one side to the other side are much lower. And the other side, suppose you want to move the domain wall from hard to the easy direction, you need more and more current when the length of this segment becomes larger. Okay? So we call this as a kind of a domain wall diode. And we can actually estimate what is the reason. We find that it is the Laplace pressure that gives us the easy and hard direction. So in the easy direction, the Laplace pressure is the same, but the hard direction, the Laplace pressure increases as you keep increasing the length and the width of this device. Okay, so by forming such devices, we can actually pin the domain valve position and we can move the domain valves clearly. So if you look at these results, for example, when the width of the larger segment is very large, we can move the domain valve only from one side to the other side, not from this side to this side. You can easily move, but you cannot move from right to left. So this is the domain valve diode device that we have proposed for synaptic applications. So to experimentally demonstrate, we created these samples with a perpendicular magnetic anisotropy. So we have used cobalt and boron, magnesium oxide, tungsten interface to create the perpendicular anisotropy. So we made devices which look like this. So we have devices with many different ratios of width. So here, if you look at this one, the ratio of the larger and smaller segments are smaller, and we also created with larger ratios devices. Okay, so now you will be able to understand what I mean. So here now we send we apply magnetic field. So the domain valves move, get stuck here, and if you apply 23 pulses of magnetic field, the domain valve move further, get stuck here. 26 pulses of magnetic field, the domain valve moves further. And this is the kind of motion that we want to achieve the synaptic state. We have also moved these domain valves by spin orbit torque. So here we apply current pulses to move. So for the devices with a smaller ratio, we need fewer pulses to move the domain valve from one side to the other side. But when the ratio of this WLWS gets larger and larger, it becomes difficult to move the domain valve. And when this ratio is much larger, what happens is that there is Joule heating, because this region gets narrower and narrower. The current density there becomes larger, and there is a Joule heating, and nucleation of the domains happen. So basically what all these results mean is that we have to optimize the pinning strength, and once we optimize the pinning strength, we can move the domain valve from one side to the other side clearly, and we will be able to achieve synaptic states. So this result summarizes that we have achieved multiple magnetization states. So if we prepare magnetic tunnel junction, basically the different positions will give rise to different resistive states. So that's about the synaptic application. Let's do some recap. Please answer this question. Okay, although I discussed only about the modification of geometry to change to pin the domain valve, we can use both. Actually, both are correct answers. Let me skip that question. Without time, let me move on to the next topic, which is about neurons. So when we talk about neurons, so the neuron should be able to achieve leaky, integrate, and fire functions. So in the case of a domain valve device, yes.
I just had one question concerning the stability of your domain valve. I mean, after applying a pulse, current pulse of magnetic field, how stable is the position of your domain valve?
Actually, it's quite stable. I don't know whether you are talking about the thermal stability. We haven't observed for like 10,000 hours or something like that, but from our observation window, it's quite stable. It doesn't come back.
Okay, and you are able to go from one position to the another easily?
Yeah. Yes, definitely. So moving forward, so when we talk about neuron in the perspective of domain wall device, the integrate is basically moving the domain wall from one side to the other side, and this is typically achieved by sending a current through the domain wall device or through the spin Hall layer, which will push the domain wall. This is not a significant issue because people have already demonstrated this in racetrack memory. And when we talk about fire, basically fire is like moving the domain wall from one side to the other side. And here we have a magnetic tunnel junction, so we receive a signal when the domain wall passes below the magnetic tunnel junction. So the read signal will be changed. So reading information using MTJ also is not very significant problem. People have demonstrated this in MRAM. But what is a specific problem for neuromorphic computing application is the leakage part. So if you drive the domain wall from one side to the other side, usually the domain wall will get stuck here, it won't go back. But for achieving the leakage function, we want the domain wall to be able to return back to its position on its own. So we shouldn't be, we can simply send a current in the other direction and move the domain wall back, but that's not what we want. We want the natural leakage on its own. That's what we want. Okay, so that's called leakage function, and that problem has been studied for some time. So we have various schemes of achieving this kind of leakage function in neurons. So one type of concept that we have studied is the neuron with an anisotropy gradient. So for example, you prepare a domain wall nanowire or microwire. Physically it will look flat like this, uniform. But if you look at the physical property, it may be different. For example, we may have a lower anisotropy field at this point. We may have a higher anisotropy at this point. So we have an anisotropy gradient. And because of this anisotropy gradient, the domain wall will return back, return to its initial position. So this is one concept that we have studied. So to make it interesting, this is what I do when I go for shopping. So there's a slope, so I'm trying to push the car, but it comes back because there's a slope. Okay. So similarly, in this case, we have an anisotropy gradient, and that pushes the domain wall back to its initial position. That's one concept, yes.
But that would also mean that the injection current will increase.
Yes, yeah. There's a compromise, yes.
That's a compromise, and if you take into consideration, then you kind of have to recalculate how much efficient the overall system will be, right?
Yeah, okay. So efficiency, we have done the calculation in that paper. So we haven't compromised on the efficiency much. So if you have to send the current from other side to reset, you spend some energy also. Okay, so
yes,
in the case of natural thing, you're going against some energy barrier, right? So you spend some energy to push the domain wall up the hill. Yeah. So we have calculated that that's not a significant problem. But the main thing is for neuromorphic computing, we should be able to achieve this leakage function.
Yes, because after it's
So that's how the neurons work. So
yes, it naturally reverses back after the threshold current. So we need to have that kind of fading memory where if we are not giving an input, it's just reverting back to its original state. And so in order to facilitate that, you created a slope that might increase the injection current, but it's still overall efficient. Is that?
Are comparable.
Comparable. Okay, thank you very much.
So that's one concept that we have done. We have executed. Second concept is using a stray field from another hard layer. Let's say this is the free layer in which you move the domain wall. So this is the free layer of a neuron. So you move the domain wall from one side to the other side. But once you remove the remove the current, the domain wall will return back to its position because of the stray magnetic field from the hard layer. So this is another concept that we have worked on. There are also some other concepts like synthetic antiferromagnetism. So one of my students presented a poster on Monday So here we have the concept of the synthetic antiferromagnetic coupling. So we have two ferromagnetic layers separated by a ruthenium layer, so there is a synthetic antiferromagnetic coupling. So the exchange field always forces the two magnetic layers to be antiparallel to each other. So if you move the domain wall from one side to the other side, once you remove the current, the domain wall will go back to its initial position because of the synthetic antiferromagnetic coupling. So because of time constraints, I will not go into the details of all this, but you can always discuss with my student who presented the poster. So let me skip many slides, because here I wanted to give you a flavor of the neuromorphic computing, how we can achieve neuromorphic computing using magnetic domain wall devices. So that's what I want to talk about. So as a conclusion, we can make we can demonstrate synaptic behavior of magnetic domain wall based devices. So in our case, we have demonstrated using anomalous Hall effect. We can actually make magnetic tunnel junction and demonstrate multiple resistance state. It's not a bottleneck, but it's very difficult for a laboratory to do this. So we are working on that. Similarly, we can demonstrate leaky, integrate, and fire functions of neurons through various configurations. To make the neuromorphic computing possible practically, we need to look at ways to improve the spin orbital efficiency, and to realize the multiple states with the significant change in the resistance value, we may also look at new solutions to improve the tunneling magnetoresistance. So with this conclusion and outlook, I end my presentation. Thank you. Any questions? Yes.
I want to ask, maybe I missed something, but maybe which part did you do to considering the weight operation? Because
weight operation. Okay, the weight operation is by the domain wall position. Okay. So in synapse, we are looking at empty J, which has this kind of shape. So let's say this is a magnetic tunnel junction with the reference layer and free layer. So depending on how much of magnetization is parallel or anti-parallel, the resistance of this device will be different. So if the resistance of, if the magnetization of all the layers are parallel within this whole thing, then the resistance will be low. So which I don't weight, low weight. If the resistance is fully anti-parallel, then the resistance is high. Then let's say the domain wall is somewhere in the middle, then you will have some intermediate resistance. So you are changing the weight by moving the domain wall. Yes.
And maybe a more general question that I also heard that from other groups, they working on phase changing material. They can also create multiple states. That is kind of similar advantage that you introduced at the beginning. You're using the domain wall motion devices to do the neuromorphic computing, but yeah, but there's also other architecture can do similar things. So what's another advantage to use the magnetic-based devices to do?
Okay. Okay, I chose magnetic material because I'm working on magnetic materials. That's one thing. That is a frank answer. But if you want to say why the domain wall devices are better, we can say considering the endurance. So if you take phase change materials, so when you change the resistance, basically you are moving the atoms. So usually the endurance is lower. So after 10 power 5 cycles, the device will be useless. Okay? So the device will not produce reproducible results. But the endurance of spintonic materials are much larger, about 10 power 15. So it's like 10 orders higher than the phase change materials. So in that sense, these materials are superior.
Okay, thank you.
Yes, just a technical question. How do you apply the magnetic field to your device? Like through a strip line, or just you put it into a magnet?
Even for moving the domain wall using magnetic
Yes.
field. So
Yeah.
we have external magnetic field.
So you apply to
We have
your
an
whole system.
electromagnet, so we place the samples on the electromagnet.
So in case of a neural network, you will need many neurons and synapses. It means you will use all domain walls with one
So
magnetic
if
field.
you are making a chip, you are not going to move the domain walls by magnetic field. So if you are making a chip, you have to move the domain walls entirely using current.
Okay.
So you make circuits. So in that case, you will have, say, probably a spin Hall layer through which you send the current. So you move the domain walls by spin off a torque.
Okay.
So only in the laboratory for convenience we use magnetic field to move the domain walls. But for practical application, we have to look at spin off a torque. Something like that.
Also, you define your weights with the resistance. Does it mean you only have positive weights in your neural network?
Can you repeat your question?
If you encode your weight with the resistance state,
Mhm.
do you also have negative weights in your neural network or only positives?
Maybe Karam can answer. Are there negative weights in neural networks? No, right? Are there?
I think so. You mean in general?
Yeah.
I think this.
In general, you have negative weights. That's why I'm asking.
Yeah, they sometimes emphasize this necessity of plus and minus weights, but then you could have transformations to make it all, because it could be also about between a reference, let's say about 0.5 is positive, right? So it's not obvious that you actually have to be negative, right? I mean, if there's a, for example, a common transformation is you're -1 plus 1, but you can make it between 0 and 1. And the role of 0, in the case of -1 plus 1, would now be played by 0.5. Are you above 0.5 or below 0.5, right? So it could be all
Yeah.
positive and still work like a
So
positive.
in the case of our devices,
Okay.
let's say fully parallel is -0.5, fully anti-parallel is +0.5, and the domain walls in the middle